When two quantities are proportional, it means that one can be expressed as the other multiplied by a constant. Take momentum, for example, which is defined as mass multiplied by velocity. So we have momentum P is equal to mass m multiplied by velocity v. Now, generally we can consider mass constant. So we can say that momentum is proportional to velocity, where m is the constant of proportionality, as we call it. So constant of proportionality. So the way we'd express the fact that momentum is proportional to velocity is with the following. We say that P is proportional, which is this alpha symbol here, velocity. Well, what does this mean? What can we take away from this? Well, if we were to double the velocity of an object, it is clear that the momentum must also double. So, similarly, if the velocity is halved, momentum also halves, and if velocity is multiplied by 10, the same happens to momentum. So I'm showing here mathematically what I mean. So here we start with P1, so momentum 1 is equal to mass times velocity 1. Now if we were to replace velocity 1 with velocity 2, which is 10 times velocity 1, then we have a new momentum, momentum 2, which is equal to m times velocity 2, which is equal to m times 10 times velocity 1. Now we can replace the mv1, knowing that p1 is equal to mv1, we can see that p2 is equal to 10 times p1. So this just demonstrates what I've been saying, where if you have two things proportional to each other, if you multiply one thing by a certain factor, say 10 or 20, then the other must also increase by the same factor. So let's take a slightly more complicated example. We start out with the ideal gas law, which is PV equals nRT, where P is pressure, V is volume, N is the number of moles, R is a constant, and T is the temperature. Now, in general, N, the number of moles, is constant because in most examples you'll look at, you don't actually have the amount of gas there is, so the number of molecules changing. So we rearrange this equation by dividing by volume on both sides and have that P equals nRT over V. Now we have two proportionality relations we can take away from this. We have P is proportional to 1 over V and P is proportional to T. So if we have a situation where T, the temperature, is kept constant, and we were to change V, then how does the pressure P change? So here I'm showing that, so we're just going to, if we're keeping T constant, that means that we can replace everything else in the equation apart from pressure and volume with the constant K. It's all constant, it doesn't matter. So now we replace V1 with V2. That is V1 multiplied by some number A. I'm making this general so that it's clear what the process is. So now the new pressure P2 is equal to K over V2, which is equal to K over A times V1 from the relationship here. So by substituting in P1 equals K over V1, then we have that P2 is equal to P1 over A. So, because we have the proportionality relation, P is proportional to 1 over V, if we multiply V, if we have a new V that is the initial V multiplied by some factor, then we find that P changes by 1 over that factor. So if V goes to A times, so V1 goes to A times V1, then the new pressure, because P is proportional to 1 over V, the new pressure will go to the initial pressure over that constant. And so we can see that actually the general rule is that if any proportionality relation we have some quantity x is proportional to some other quantity y to the power of some number, any number at all, let's call it a. So if we have that x is proportional to y to the power of a, then if we change y by a certain factor, then x changes by that factor to the power of a. So if we have that y goes to, let's call it by, then x goes to b to the power of a x. Okay? So let's take another example, shall we? We'll go with Stefan's law, which is the amount of power emitted by a black body, and that is given by P, the power, is equal to sigma, which is just Stefan's constant, A, which is the surface area of the black body, multiplied by T to the power of 4, where T is the black body's temperature. So what if we have, how does the power compare between two stars where one star has twice the temperature of the other? So T2 is equal to 2 times T1. How does P2 compare to P1? Well, using the rule from before, then if we have that P is proportional to T to the 4, because sigma and A are both constants, because we don't expect a black body to change in size, then using our rule from before, we should have that T2 is equal to 2 to the power of 4 times T1. 2 to the power of 4 is 16, so T2 is equal to 16 T1. Now, just in case you may not like the how I've shown how proportionality gives these relations, I have another explanation. So we have say x is proportional to y to the power of a. Then we have some x1 and some x2. Now x1 is equal to k, some constant, because it's proportional to y to the a, so k times y to the a and y1 to the a, and x2 is equal to k, the same constant, times y2 to the a. So if we were to divide x2 by x1, then that gives us x. Yeah, sorry, I wrote that slightly wrong. What I mean is P2 is equal to P1 multiplied by T2 over T1 to the power of the proportionality power, so 4 in this case. So, as you can see, if T2 is twice as large as T1, then we have that this is equal to P1 times 2 times T1 over T1 to the power of 4. Those cancel, and we have 2 to the power of 4. Again, 16. So one more important thing about proportionality is that if you are giving an initial value for a variable and you know the other variable's proportionality, then no more information is needed to calculate further values. So to make this clearer, consider some completely unspecified equation for the energy of an object, and all we know is that the energy is proportional to this object's volume. Now, I don't even know what quantities out there are actually described like this, but we know that the initial energy of the object is 10 joules, so E1 is equal to 10 joules. So if we are told that the volume is doubled, then we instantly know that the new energy is just twice the initial energy. No more information is needed to work that out. Again, taking another example, we have that the velocity of an object is proportional to its length to the power of 2/3. Absolutely no idea why, but what we're told is that it starts out with it has a velocity initially of 10 meters per second, and then if we're told that its length increases by a factor of 8, so the new length is 8 times the old length, then we know that v2 is equal to its initial velocity multiplied by 8 to the power of 2/3, which actually is just 4. So we know the new velocity is 4 meters per second. So kind of the point of all this is that it's a much preferable alternative to putting all the information into an equation a second time. If you're given a list of values that you need to put into an equation, so say you have an ideal gas question and you need to work out V, the volume given a pressure, number of moles, and a temperature. Then if you're just told that one value doubles, you don't have to put everything back into the equation again. If one thing doubles, all you need to know is the proportionality to be able to get the new value. That is the point of all of this. It also relates to the common sense video that I made, where if you know the proportionality of something, then you know how one thing behaves based on the other. So let's go back to my completely random example that the velocity of an object is proportional to the length to the power of 2/3. Now I've completely made this up, but from this relation we have that we expect as length increases, then we should have that the velocity also increases. Or if we had the velocity is proportional to length to the -1, or 1 over length, then as length increases, then we should expect the velocity to decrease. This knowledge allows us to remember certain equations just by thinking about them with a little bit of common sense. I go into more detail about it in my other video, but just very quickly, it means that if you've written out an equation, you can look at it and think, right, well, here I've written that apparently in this system velocity is proportional to 1 over length. But then when you actually think about the physical system, is that really true? Do you actually expect the velocity to increase as length decreases, or for the velocity to increase as the length increases? Is that actually true? If it isn't, then you've written the equation wrong. And so this is a good way of checking whether you've written out an equation correctly. Now I hope you found this helpful, and thank you for watching.